Hello, good evening, everyone, and welcome to this special ICTS distinguished lecture. For those of you who haven't been to ICTS before, let me just tell you a little bit about ICTS. It's a very new center, as you can see. In some way of accounting, we are 10 years old, but in another way, we moved to this campus 3 years ago, so we are 3 years old. But the campus, after moving in, of course, also went through a period of evolution, and in a way, everything got operationalized only in December last year. So from that point of view, we are 6 months old. But anyhow, we are very new, and we also take that newness seriously in the sense that we try to do things differently from other institutions. In some ways, our mandate is very different also from other institutions in the country. We have a core research group in various areas, in theoretical physics, in mathematics, quantitative biology, and so on. But apart from that, we organize these programs which you are part of, and in that way we are modeled on places like the KITP in Santa Barbara, or the ICTP, or the MSRI in Berkeley, and so on. The programs are a very integral part of ICTS, as you might see from looking at our calendar on the website. We have programs throughout the year. And the weather in Bangalore is such that it's very nice to be here through much of the year. So the programs span a variety of topics, not just those in the areas which we have research capability, but a much wider area. In fact, things have ranged even into areas of even things in finance, and of course computer science, and so on. So, but largely in theoretical physics, quantitative biology, and mathematics. But even in those subjects, not necessarily in areas where ICTS people do research. So the program proposal is very open, like at the KITP and so on. And anyone can submit a proposal, and now we are moving to a system where there is a time window. For instance, now till December, we are accepting proposals for programs to be held from March 2020 to September 2020. And then this program, this call for proposals will be open till December. Then for the next 6-month slot, we'll open out from January till June, and so on. And these are vetted by a program committee, and the programs which are selected, of course, one works with the program organizers on doing that. So ICTS is not a passive host of programs. We actively shape the programs. We try to solicit programs in different areas where we think we need to build capability, especially in India, in areas where there isn't probably enough expertise or enough again, capability. So, we kind of have many of these things at the back of our mind in curating the programs that we do at ICTS. So that's an integral aspect of ICTS. Finally, we have a vigorous outreach program and a lot of public lectures, both at ICTS and often in cooperation with many other institutions in the city. We run a monthly lecture with the planetarium, which has been very popular, called the Copy with Curiosity, in which we have scientists, and that's a sense in which we often try to integrate it with our programs. Many program visitors have often given lectures in that popular format as well. At the planetarium, we have the number of other science outreach activities also that we do, including planning for a sort of a mega science festival in 2019. That's a sort of snapshot of what ICTS is. The ICTS Distinguished Lecture is a very special lecture in which we invite eminent scientists to talk about a topic of course, on their research, but which also is something which would be of appeal to students, researchers from a wide variety of areas. And we are very happy today to have Professor Coppersmith speak today on quantum computing, something again which India, like many others, is planning to invest in a big way. But I will let Professor Bulbul Chakravarti, who is organizing this, is one of the organizers of this program here, and visiting us as Simon's visitor on sabbatical at ICTS. I'll let her introduce Professor Coppersmith.
Okay, so I guess I'm an honorary member of ICTS for this semester because I'm here on sabbatical and I am one of the organizers. But I guess the main reason she asked me is that I'm probably in one of those rarefied stratas where I have crossed 60. I have known Sue probably I've known her for a long time and probably longer than most people here. So as Rajesh said, this particular seminar is reserved for distinguished scientists, and Sue Coppersmith certainly is an eminent scientist, a theoretical physicist. She's a member of the National Academy. She has many, many other honors that if I try to list them, then I think, the time for her talk will get cut short. But she has made seminal contributions to many, many different areas of finite matter physics, mostly in disordered and driven systems. So she started looking at driven disordered systems way before most of us did. But more recently, she has been looking at quantum computing, and again there, she has made contributions that has changed the field. So I think that's her hallmark, is that she sets sort of trends, she changes the direction in which fields move. So with that, I'll just give the mic.
Thank the Institute for giving me the opportunity to come, and I've been participating in the entropy workshop, and that's been wonderful for me because I did work in very, very closely related fields for a long time, and it's great to see the progress that has been made, and the lectures have been really outstanding, and it's been a great, great opportunity and a great experience for me. But I did want to talk to you about the work that I've been doing lately, and that's about quantum computing. And in particular, I've been working on making quantum computers out of silicon. So this talk will be a little bit of motivation about why we think silicon is a good platform for making quantum computers, and then sort of the goal is that you can sort of see what the problems are and the kind of thinking that goes into solving the problem. So again, what I'm going to tell you about is mostly about silicon, but you'll see in terms of the hardware the kind of work that needs to be done in order to make a quantum computer that works. And you've been I'm sure hearing about it because it's been in the news. But you'll get a sense that the progress has been tremendous, but that does not mean that you'll have a quantum computer in your pocket so soon. But still, you can get a sense of how things are progressing. Okay, so again, I work at the University of Wisconsin-Madison. I work very closely with an experimentalist named Mark Erickson, who's a professor there, and he has some of these people have moved on, but he has a reasonably substantial experimental group, and then also on the theory side, everything I'm going to talk to you about was done really in pretty close collaboration with Mark Friesen, who's a research scientist, and then here are the students and postdocs, and everybody will be mentioned at the right time, so at least you'll have a sense of who everybody is. The group overall has gotten funding from lots of different places, but this continuing funding has been from the Army Research Office. All right. So again, the first part is to motivate why people are so interested in quantum computing and why, in particular, silicon has been of interest and is becoming of more interest lately. And I think the best way to motivate it is to just discuss classical electronics, and I will talk mostly about in terms of trying to reach out and make things familiar. Talk about phones. And the point is that I guess the transistor was invented around 1950. There was a transistor radio for sale in 1954, which was before I was born, but not by much. But anyway, I had 4 transistors, and it cost $50, which was equivalent to $427 in today's money. All the dollars will be U.S. dollars, but I tried to do conversions, but it was late, and it was too much for me to convert everything. So it's all dollars. But it's all relative, so it's all good, right? Okay, and so then I looked. Now, I did not take the most recent iPhone, which is $1,000, but has 7 billion transistors. But I went a few generations back because, the latest one, as you know, is sort of jacked up in price. But if you go on eBay, which I did last night, you can find an unlocked, very important to be unlocked because otherwise, it might be subsidized by the carrier, unlocked iPhone, and also not refurbished but new for $399.49. And that has more than 3 billion transistors, and again, for less money. Okay, and as we know, I think it's reasonable to think that once you change things by, a factor of 1 billion, it really is different. Even though there's a, direct line of, continuous improvement of transistors. This only goes down to 1970. This is 1,000 here, and this is 20 billion up here. And again, there are points like everywhere on this line, but just, computers keep getting, keep getting better and better. And so we've gone, again, 9 orders of magnitude. So take that, particle physicists. And again, the way this has done, there'll be many things about the particle physicists that we're big. It's like, we don't feel big in condensed matter, but we are big. Okay. So, and again, this was done almost entirely just by reducing the size of the transistors. Now, this is not done to, oops, I didn't mean to do that. This was not done to scale. This was done in PowerPoint by drawing lines. But the whole point is that the entire way that we went from 4 to 1 billion was just by putting more transistors in the same area. And in fact, the chip in your iPhone is like, 10 millimeters. It's like a square centimeter, roughly speaking. So, no, I'm sorry. This is 5, just work it out. It's like this big, but it fits in your phone, obviously. Okay. So, and so basically, we just keep making things smaller and smaller. And so then I have some pictures of, these are fabs that I found on the internet. These are TSMC is the company that makes the transistors. These are for the iPhone 8. They're 10 nanometer transistors, and this is for the new ones that were just announced, the iPhone XS, and those are 7 nanometers. And what's amazing is if you go back to I didn't take the curve. I took a curve out. This thing, if you look here, then you go along this line, and you see this is from 2010, and you keep going, and they're like right on the curve. Okay, that 7 nanometers in 2018 is like exactly the right place. Okay, so that's how computers have been getting better since 1950. But we know for a fact that this has to run out of gas. And now it is true that 5 nanometers is going to happen, and they believe 3 nanometers is going to happen. But you're sort of stuck at a certain point because this is a picture of silicon. This is a scanning tunneling microscope image, and and those are the atoms, and they're just once you get down to 1 nanometer, there's only one atom there, and something has to happen, right? And so, and again, we've only had one trick, which is to make things smaller and smaller, and we've been able to get factors of billions out of it, but at a certain point, that's going to end, and it's pretty clear that there's sort of no getting around that. So here's the picture, and again, this is my other dig at particle physics, that this is going to happen before the next particle accelerator is built, where you really hit one atom. And so then the thing, well, what do you do? Okay, and that is one of the motivations for quantum computing is, the knowledge that, creating computational capability has the potential to really change how people live. And so people want to keep doing that. And again, the standard way, or in some sense the only way that we've done that so far, is by making things smaller. And at a certain point, if you make a computer out of atoms, going smaller is not going to be feasible. Okay, so that is the motivation. But then the other thing, of course, is that as things get smaller, the quantum effects become more important. So it's sort of natural to say, well, can we harness quantum mechanics to make computers more powerful? And I decided I have a talk where I talk more about quantum computing. I'm going to assume that you've heard of it and you understand. You're using quantum coherence and superpositions, and it is known that there are some problems that we believe we can solve much more efficiently in quantum computers, using quantum computers. And it turned out that sort of the first interesting problem of that type was what's called Shor's factoring algorithm. And that's just a thing where you take a big number and you know it has two factors and you want to find the factors. And it turns out that classically the best known algorithm takes a time that scales exponentially with the number of digits in the number. And Shor in 1994 presented an algorithm that factors in polynomial time. And that sounds like a pure curiosity until you realize that all of cryptography is at the moment is based on the difficulty of factoring large numbers. And so I like to remind people, the old people, and then the young people, this is like a new fact, but I am old enough that when I was in college, there were not cash machines. That's thing number one. And thing number two is if you went to a store and you bought something with a credit card, to check your credit card, they called up the credit card company and read them your number. Okay. And the fact that you can buy anything on the internet or use a cash machine is due to a thing called public key cryptography, and the thing that makes public cryptography work or secure is the difficulty of factoring large numbers. Okay, so when Peter Shor did this, there was, a huge amount of, oh, gee, if we get that, well, okay, so it turns out that the NSA, the money that we get from the Army Research Office, actually comes from the National Security Agency, and they were like, oh, we can break encryption, okay? And then actually people in Citibank are really interested in a more defensive thing because they don't want to wake up one day and find out that they've lost $1 trillion. So that did create interest. Okay. So, but that also tells you why our funding comes from the NSA, because this is their main interest is in cryptography. So they want to make a really big quantum computer that will run Shor's algorithm. Because again, I'm not going to tell you details, but to really be able to break into banks, you need a big quantum computer. And the whole point of, and this is all the different ones, sorry about that. The whole point of our making it in silicon is billions, no problem, right? In principle. So that's why we did this. Okay, so again, there's like a lot of work on quantum computing. I would say the leading technologies at the moment are superconducting qubits and ion trap qubits. But if you think that the ultimate degree of scalability is going to be a serious consideration, then that is a motivation to look at silicon. Okay, so that's what I'm going to tell you about is our work on making qubits out of silicon. And so here's a artist's rendition of how they work. And essentially the point of this technology is, again, it's as close to current classical electronics as you could imagine making a quantum computer be, all right? And so the way it works, now our particular implementation, the silicon is this little thing here. So it's actually sandwiched in between silicon germanium. There are electronics, commercial electronics today that are made with silicon germanium, but your phone is not, but there are commercial electronics. So it's known how to scale it up, et cetera. It has advantages from the point of view of reproducibility because the oxide is a source of defects and the electrons live in the silicon and they're a bit away from the oxide. Anyway, but you can just think I have a layer of silicon, and then I have metal gates on top, and then I apply voltages to these gates. And by adjusting the voltages appropriately, I can make what are called quantum dots. Quantum dots are just little, you've arranged the voltages so you've got a region with one electron in it. Or one or two or three, you can control it. You just change the voltage, you change the number of electrons. And so all the data I'm going to show you are done on a device that looks like this. There's a dot here and a dot here. So it's going to be one qubit made out of what's called a double quantum dot, because there are two little puddles, two quantum dots, and then you can couple them. And again, all the manipulations are done by changing voltages, by just adjusting these adjusting these gate voltages. I think I'll tell you now that when we say, oh, we measure the qubit, there's a question, well, how do you do that, right? Okay, and the way you do that in this particular architecture is you run current through what's called a quantum point contact, okay? And we can think about like moving a charge on the right, then it's negatively charged. It closes down this channel slightly. And so the current, when you apply voltage, is a little less of the electrons on this side than that side. So in the end, when you manipulate qubits, you apply voltages and measure currents. That's all we're doing, okay? But then, of course, there's this, you're moving an electron around, and but it's all done just by measuring. By applying voltages and measuring currents. The architecture that we use is really based on an original suggestion 20 years ago now by Loss and DiVincenzo, and so they were the first to to use quantum dots. Okay, and I said this in words, but I have a picture, so I'll show it to you, and I'll mention it again. Is that and actually, I should tell you, the first really good qubit in silicon was developed in 2014, okay? And the first really good qubit was probably, at least 10 years before that. And when people would say, well, you don't have your qubit yet, why are they giving you money? And the answer always was, again, this possibility of scale up. So again, the architecture, the metal on top of semiconductor with an oxide in between is exactly what you do to make classical electronics, okay? And now that the qubit's working, then we can say, oh, look, now it's just a matter of getting more qubits working and to do the scale up, and we can leverage the investments that have been made in classical electronics, hopefully to do the scale up, okay? All right, so that's the motivation for the work that we're doing, but what I'm gonna tell you about is the first qubit that we got working, okay? And how we've been working to improve it. Because one thing that we know is that in order to make a quantum computer that actually works, you have to make very, very good qubits. Again, I'm not going to tell you details about that. That's like another talk. But essentially, you need, in order to do error correction, this was another one of Peter Shor's great contributions, the fact that you could do error correction in a quantum computer. But in order to do the error correction, you have a very small error budget. And the lingo for how good the qubit has to be is the quantity that you need to optimize is called the fidelity. And the fidelity really needs to be at least 99%. Okay. But the fidelity is all errors. So if you have control errors, you know, whatever. So, but there's a fundamental limit on fidelity, which is just the coherence of the qubit. Okay, and that is, again, you know, keeping this quantum coherence going for a really long time. And that's the figure of merit that I'm going to use, which is basically, this is the quantum coherence time. But then you have to count gate operation times. So it's really easy to make a really long coherence time in a quantum system just by isolating the system, okay? And in fact, if you isolate a system, it, you know, the coherence times of many seconds have been fabricated. But the thing is, you also need to make known operations to manipulate the qubit. And there's this sort of tendency, like if you can get in there and you can manipulate the qubit, then unwanted noise from the environment tends to also get in there. So, you know, so you can get fast gate operation time, but if you do, you tend to have short coherence times, and you can have long coherence times, but then they tend to be slow. And so that's the trick of how do you get a really long coherence time and still be able to manipulate it. Okay, and again, when we say, you know, we need a high figure of merit, really at least 1,000 would be better, but 100 is like absolutely minimum. Okay, and that's the thing that you're trying to do. Okay, and so in this field of semiconducting qubits, there are several groups working and more going in. As unfortunately, like if you do something that seems to be working, then you get more and more competition, but that is life. It's success, I suppose. And so you need an angle. Okay, and our angle is that most of the groups are thinking about making the coherence time longer. And we said, oh, we have to do a ratio, right? And everyone else is working on the coherence time, the numerator, so we'll try working on the denominator. Okay, so that was our brilliant idea, was to work on the denominator. But there is an idea, and basically what we did was that we came up with a qubit that is, we call it a hybrid qubit because it has a pretty long coherence time, sort of a normal coherence time. Not super long, but not super short, but a really fast gating time. And we did that by making a qubit that was, that you can view as a hybrid between a charged qubit and a spin qubit. So spins tend to couple really weakly to the environment, and charge you can manipulate really fast. And so by being able to switch back and forth, we were able to get somewhere. Okay, and so basically, that's what I'm going to tell you about. All right. Now, I think I probably won't get into the details of all the things. Okay, so what we did is we made the qubit and it sort of worked, and that's what I'll show you. But then it turns out that, like, if you just do it, you get something which is not high enough fidelity, and or the figure of merit is not high enough. And so then was the real work of like, okay, how do we really optimize a qubit? And I think I will not tell you every detail, because I don't want the talk to go on too long, but I'll just sort of show you what we're able to do. And I just want to give you some idea of like kinds of things you have to do in order to make a qubit. Okay, so when I show you everything, I'm going to do it by showing you plots that, roughly speaking, all look like this. Okay, and so basically, like when you're actually running the quantum computer, okay, I'm talking about a qubit, and it turns out that you can think of a qubit as a spin, and you're applying gates, which means that you're rotating the spin by precisely known amounts that you tell it. Okay, and in practice, you only really ever move the spin by at most pi, right? You know, usually pi over 2, or you know, some small fraction, but you know, if you just look at pi over 2 rotation, if you're, you know, anywhere near to being good enough fidelity, it will look perfect by eye. So the way we see whether our qubit, how good our qubit is we sort of set it going in some rotation, and then we just let it keep rotating, and then we ask, well, how long does it keep going before it decoheres? Okay, so this is like, for instance, that you have, if the spin, you think about the spin being up, and again, we set it rolling, and so here we're measuring the Z component, and if it were perfect, it would just oscillate forever, the sine wave, but it decoheres, and so it decays, and so you'll usually see grayscale plots, and then you'll see like stripes. And the way you know how good your figure of merit is you just count the stripes, okay? And again, we need 1,000, all right? And you know, we need at least 100, and really we need 1,000. Okay, so before we got our qubit really working, this was the state of the art in silicon. And this is an experiment that was done at a research lab called HRL Laboratories. And it was a state of the art, got published in Nature, you know. And here you can see that, you know, they're measuring their qubit, and here it's going, you know, it's rotating, you know, okay, it's going like this, okay? And so you can count, right? 1, 2, 3, it's less than 20, okay? Sorry. Okay, and so then then we finally got our hybrid thing going, and it looks like this, and you can see that it's really a big improvement. Okay, and so this was, and actually, you know, at 300, and we're like, great, this is really great. Okay, but then there was another thing about that qubit, the one that we, you know, brand X for us, and that was that in order to really make and we're still making in this talk, we're just going to make the first qubit. Okay, that you have two ways of rotating. And again, you think of a spin, and one way is you can go this way, you can do longitude, or you can do latitude. Okay, and the oscillation I showed you actually was the latitude. And for the longitude, they actually did not get it to rotate one whole rotation. And what we were able to do was this. Okay, so this is the grayscale, but here's the line cut, and here you can see that it oscillates. So again, it was considered a great advance. But on the other hand, it's clear that that's like nowhere close to 100 oscillations. And so you can't move forward until you get 100. All right. And so basically, I think I'll tell you just about how we got from here to here. Okay. And this one is actually, if you count pi over 2, so it's 25 2 pi's, but if you say a gate is pi over 2, then it's up to 100. Okay. Now, and again, this might be marginally good enough, but, you know, we want to do better. And so the part of the talk that I'm not going to give you so that we can eat is about what we're doing to do better, but I'm only going to show you parts that have been demonstrated experimentally. Okay. Yeah. 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 Yes. So this is the number of rotations within a coherence time. And again, you can sort of see that's going to be about 25. Okay. So it's nice. Okay. And again, then there's a separate question of like the control electronics and making sure there isn't pulse distortion so that the actual gate is at 99%. And I'm not addressing any of that. So that's why I'm trying to be honest. Because if there was a specialist in the audience and if I had said that was the gate fidelity, they would immediately start yelling at me. Okay. Yeah. That's exactly what you do. Yes. Okay. Did you hear the question? So again, this thing of this is, I mean, there are different ways people do it, but with the way this experiment was done is we started in a known state, okay, and then we go for that time, we measure, okay, and then the next thing we go for a lot, and then we do that a lot of times to get good signal to noise. Then we go to the next time, okay. And again, all the actual measurement is you're just measuring that voltage down that point contact, okay. So it's just a voltage measurement, but it's, you know, it's one electron, and so it has very susceptible to noise, and it's at low temperatures, and in the meantime we're driving this thing like crazy, and you know, so it's a very non-trivial experiment, but in principle it's very easy. Okay, so we're theorists here, so simple. Okay, anyway, but these are all data. Okay, and you know, this is an experimental paper. Okay, so I just want to give you an idea of like what the idea and how sort of what the thought process is. And I will say that a lot of what I'm going to tell you was sort of adapted from superconducting qubits. It's not the same. If you're interested, I can tell you a little bit about what they did and how it was very, very clever. We were able to take certain parts and adapt it, and and help our qubit. But the general thing of like, how do you get in there and make the noise not decohere the qubit? That's the key. Okay, so first I'll tell you what a qubit is. All right. So it's just a two-state system, and there are sort of two sort of simple things that I'm sure you're used to thinking about that you can think of as a qubit. And the one is a spin, okay? And so that's what I've been doing with my fingers, talking about a spin. But when you're in semiconducting qubits, it turns out it's a little easier in terms of relating things to experiment to actually think about it in terms of just an electron that is in a double dot that's tunneling back and forth. And they're mathematically equivalent because it's like there's a left and there's a right, and then there's the tunneling in between, and then the Hamiltonian is a 2x2 matrix, okay? A Hermitian 2x2 matrix. All right, if it was a spin, you'd have a parallel magnetic field and a transverse magnetic field, and the Hamiltonian would be a Hermitian 2x2 matrix. So there's a one-to-one correspondence, okay? So when I talk about the spin and talk about the double quantum dot, it's the same mathematically because it's just a 2x2 matrix, okay? And yeah. Well, it is exactly the same because I'm not talking about the eigenstates, I'm talking about the Hamiltonian. And so then you have linear combinations of the linear combinations of each side are the eigenstates. But that's the same as saying that, in a field, if my field is in this direction, plus z and minus z are not the eigenstates. Okay, so, yeah, okay. And again, this is for the, okay, so that's all I'm saying, okay. Yeah, so these are the basis states, and then there's an off-diagonal term. But think of a spin that's in a field that's not parallel. Okay, and then it's exactly the same because if these are not plus and minus, you add a constant to the Hamiltonian. Okay, and so that it's plus and minus, and then and if this is imaginary, it turns out that for a single qubit, it makes no difference at all. Okay, yeah. Well, no, I mean, that's as far in the talk as I'm going to get. He said, okay, there is a qubit that you can do like that, which we've actually made, but that's not what the qubit is. Because again, it actually, yeah, that's a great point, okay, is it that what makes it hard to actually describe what's going on often is that you're using what's called a logical qubit, where you're using two of the states. And, and there's like a subspace that is this 2x2 Hamiltonian, which is what you're interested in. But the actual system is bigger. And that's our actual thing that we got working is like that, where I'm going to try to carry you along so you get a sense of what it is. Okay. But the thing that it will be easiest, I think, in terms of visualizing is to start with a charged qubit. Okay. All right. And again, the trick of all of this is that the delta and the epsilon, the tunnel barrier, and this thing, this is called the detuning, this difference in energy. Those you can control with voltages. Okay. You just apply voltages and they're totally arbitrarily adjustable, and really fast too. We can gate this thing at gigahertz frequencies. But again, you want to do that really fast in a really precise way without coupling to any other charge noise in the system. And that's what makes it hard, okay? Okay, so this is the Hamiltonian here. And it has two energy levels. Here are the eigenstates. And well, here I cheated, right? Because here it's left and right. And they're not. They're linear combinations of left and right. Okay, and here are the energies. I'll have to fix that, sorry. Here are the energy levels, and you've solved this, 2x2 matrix. Okay, here are the energy levels. Okay. And actually, this qubit was the first qubit that was implemented. This is a superconducting qubit from 1999, okay, which you can go look up. All right. Now, it turns out no one uses these qubits these days, and the reason is that if you just did the electron going back and forth, it's very susceptible to charge noise. And in this implementation, it's slightly different for the superconductors, but similar enough that everything they did we could steal, with attribution, of course. The thing is that that you will have charge noise. And it's known now, this is a very nice experiment by the QUBIT group, where they really went in detail and showed that the dominant effect of charge noise is that it causes fluctuations in the detuning, in the difference in energy between these wells. Okay, and so what happens is that epsilon fluctuates, and so what happens is that, these parabolas are like, drifting back and forth on typically a fairly slow timescale, but it's a 1/f kind of noise, and so there's a broad range of timescales, but the longest ones are quite long. Okay, and so what happens is that, so that sort of parabola, the square root of the parabola, but it's sort of a parabola. The parabola is sort of drifting to the left and the right. The qubit frequency is just, this energy difference divided by h bar. And so it's fluctuating up and down, okay? And fluctuating up and down is a source of decoherence. It's called dephasing, and it's one of the sources of decoherence. Okay, and so the obvious thing to do is to say, well, I mean, if you're out here, it's like a catastrophe. But here, if you're near the minimum, then you say, well, to first order, you're insensitive to those fluctuations, and you should do better. And indeed, you do better. And that actually was the first, qubit that had like a fair number of oscillations. And this is what was called quantronium in the context of superconducting qubits. And actually, believe it or not, in the silicon qubit, actually in any semiconducting qubit, we just did this a few years ago, went there, and then we drove it. And it sort of works, except you can see that you're nowhere near the coherence that you need. Okay, you just don't, I mean, this is like 5, right? And this one might be 8. And again, you need, hundreds and hundreds, preferably thousands of oscillations in order to move forward. Okay. So, and again, we didn't think of how to do that better. So, but, we wanted to do better. So this is what we did. And basically, again, the key here is, we don't get rid of the detuning fluctuations. We just sort of assume they're there and they're going to be a problem. But you say, well, we have a sweet spot, this place where the derivative of the energy difference is 0. Well, let's just try to make the sweet spot better, okay? And this was, again, really first shown to be a really good strategy by the superconducting qubit people. So this is the Yale group, Sholkoff and Gervin and Devray. Okay, so we went down their path of ideas. Okay, and so the idea is to try to make it so that we're less sensitive to charge noise if we think about it as a charge qubit. So as I did it now, it's a charge qubit with a fast gating time and a terrible coherence time. So this way I'm presenting it to you is like, well, we're going to try to keep the really fast gating time but get the coherence to be better, okay? And again, so this is our thing, and it's related to previous work, but I'm not going to tell you in any detail. So I just want to tell you what the qubit is, because that's sort of the only idea, more or less. And so now it's going to be more complicated. We were actually going to add electrons, okay? And now here's where you'll see why we think it's a hybrid, okay? So, and so we have 3 electrons and 2 quantum dots. And what I'm going to show you is that you can manipulate it fast, and now we're going to think about it as a spin qubit that we can manipulate fast. Okay, so here are the states. Okay, so you have a double dot, and one side has 2 electrons, and one has 1 electron. And one way to think about the qubit is that in the double dot, you can be either in a singlet or a triplet. Okay, and now I will tell you that I lied a little bit about this triplet. This is the actual triplet. These are states where if you have this electron, you see how the electron and the other guy is different, they have the same spin quantum numbers. So if you just look at the left, it looks like a spin qubit, but all the spin quantum numbers are the same, okay? And so what that means is that you can gate it, you can do the operations just by moving electrons around. So I have an animation to do this, okay? So here I am in state 0, okay? And again, this is a two-state system. I've got state 0. And now I'm in state 1. Okay, and I moved the electrons. I didn't actually flip any spins. And then another way to do it, this is the way I thought about it all along, was this way, where, okay, I start in the singlet. Well, I can do it. Yeah, I start in the singlet. And then I move an electron to the other dot. And then I move the other one back. And now I'm in the triplet. And again, the key here is that here I'm thinking about the spin, the qubit is essentially being a spin qubit, but I can move between the spin states by moving charges around. Okay, that's why it's hybrid. Okay, so now I just want to show you how it's done in the experiment, and then I'll try to stop on time. Okay. Oh, I didn't mean to do that. I meant to show you this. Okay, so this is a electron micrograph of the device, but all the letters and the little dots that are supposed to be electrons were added by PowerPoint. Okay. Okay, and these X's are the leads. Okay, because remember there's this quantum point contact. And so you put in you apply voltage here and you measure IQPC as a quantum point contact current here. So you measure between here and there, okay? And then there are these gates, and all the experiments were done by applying pulses to this gate called L. L is for left, just so you know. And R is for right, and M is for middle. T is for Tom, and then the P is for a thing called plunger. They always call these gates plunger gates if they're in the middle. Okay, there's also a point contact on the left side, but that one never worked, so you could ignore that. Okay, so it's a real device, and so when I draw these energies, this is energy versus detuning. That's the standard diagram you do in semiconducting qubits. These are real energies that we measured experimentally, okay? And so basically, here, I'll just put in all the transitions. Okay, so we're actually going to run the qubit on this side. Okay, and this is this is R is for right here. Okay, so this is the energy splitting between the lowest two states on the right side, the singlet down here and the triplet right here. Okay, and then and they just go up here, and they have this slope because we have two electrons on the right. Okay, in these states. Okay, and here we have states with two electrons on the left. It happened in this device, it's called the singlet triplet splitting. The singlet triplet splitting is much bigger on the left than on the right, which is handy for some things which I'm not going to tell you about, but it just is. Okay, but I'm not going to talk about anything that happened there. Okay, and what I showed you before was like I can move electrons from the left to the right, and there was no problem. And so all of these crossings turned into anti-crossings. Okay, so if the tunnel coupling were 0, this would just be a straight line this way, but it turns into an avoided crossing. Okay, and now here, this is why I want to tell you about the charge qubit. If I just look here, it's a charge qubit, okay? But what I'm going to do is I'm going to be like working out here. So it's basically here it's a charge, here it's spin, and by moving back and forth, that's how that's how you get the hybrid nature. Okay. Okay, and that's just the part that we're going to use, all right? And so everything in this talk, what we did to do the operations is we applied an AC voltage to that gate LP, and what it did is change the detuning. So you drive the detuning at a frequency that's resonant with this energy difference, and basically then you do Rabi. You do Rabi oscillations, and then it causes coherent oscillations. There is this thing called the leakage state, and again, you need the leakage state, or else that singlet and triplet would have different spin quantum numbers. But because it's mixed, it's it's mixed in, and so you can make transitions. But when you're doing it, you have to be careful not to get leakage into the leakage state, because that's bad for your qubit. Okay. All right. So what to say? I think that was right. So yeah. But then the other point is that here we are out here, and if our qubits out here, then the energy of the singlet and the triplet are very similar as a function of detuning, because these lines are parallel. It's basically, in both cases, you have one electron on the left and two on the right. And so when I change the detuning, it's fluctuating around, right, because of charge noise, but the two states go together. And because they move together, the qubit energy stays about the same. And that's how you end up with longer coherence time, even though we can gate it as if it were a charged qubit. Oops. Okay. All right. So that was the what I showed you before, and that was the first time we ran the qubit. But then I will tell you how we managed to get that factor to get it up to 100. Okay. And basically what we did here is this is where we were. This is all the data I showed you before. The energy levels of the qubit looked like this. Okay. And again, we operated it here with AC by applying an AC voltage. But the thing is, if you actually just look at the qubit energy, though, the energy as a function of detuning did this, all right? And again, the trick was that you needed to mix in that leakage state in order to get a matrix element, all right? And so what you wanted to do is you wanted to go to the left, okay? And if you go to the left, then you mix in more of the leakage state. But on the other hand, you can see that the qubit dispersion is no longer flat, but it goes down and then it goes back up. And after like a year or something, an amazingly long time, we realized if we change the tunnel couplings, this is just, we took all the other parameters the same and just made the tunnel couplings different, then you can see that you can make it where the qubit energy as a function of detuning is much flatter. And in particular, you can operate it at much smaller detuning, and that makes the matrix element go up, and that makes the qubit frequency go up. What's called the Rabi frequency go up, the rate at which you can do your operations. Okay, and so that's how we got from this, which again was our original qubit, to this. And now I'm going to tell you a little more about like what it's like to do a qubit, because basically you do an experiment, you see where you are, you figure out what your biggest problem is, you fix it, and then it turns out there's another problem that was just not as big as the problem you fixed, and then you got to fix that. Okay, and that's what you do. Okay, yeah, yeah. Yeah, but see, well, here, let's look at this one where it changes. Okay, so what happens is that, and again, it just happened. These were just like, they applied voltages and then they measured, and this is what they got. Okay, this was just done. You get an experiment that works, and and then you stop. But then you realize that you're not done. Okay, so again, here's your singlet, triplet. Okay, but then this guy runs into this anti-crossing. This is a really big tunnel hole. Yeah, the upper one is the charge. Okay, and again, there's another state out here, but it just happened that on the other side, the singlet triplet splitting was much bigger, so we could ignore it. Okay, so it runs into this anti-crossing and it gets pushed down. Okay. But if you make this one bigger and this one a little smaller, then basically you just make it doesn't get pushed down anymore. And if you tune it, which you can do, because you can do everything's voltage controlled, then you can make it really very flat. Okay. And so then it really was a matter of just like getting this Brunder, the graduate student, to, he just tried a bunch of things. I mean, after a while you sort of get a sense of what it does, but that's what happened. Yeah. Well, okay, so I have everything is like months of my life. It's wonderful. It's all flashing before my eyes. So here you're doing AC driving. And so so again, if I compare to superconducting qubits, they have various, so the thing that you're comparing to is a harmonic oscillator where the energy levels are uniformly spaced. And there, in a superconducting qubit, they might have only a few percent anharmonicity. Where here, you can see our anharmonicity is like a factor of 3. I mean, it's huge, So on the scale of qubits, this amount of anharmonicity is like a picnic. You know what I mean? Because basically you use the frequency selectivity. Okay. Now, I didn't tell you about this, but our first implementation of the qubit, we did what's called DC driving, and there leakage was our dominant problem. That's why we went to AC driving, because the leakage was a big problem. Okay. But when you do AC driving, you're much more resistant. Yeah, you're much more resistant because the frequency selectivity helps you tremendously. Okay. But yeah, that was our first idea. And then we realized, leakage, if you do it this way, leakage will kill you. So then we said, okay, let's do AC driving. And then, but that's just to give you some idea of like what we do for a living. Okay. So this is the thing that led us to think that we should be able to do much, much better. And this is data that Brunder took. And what he did was he was way out here, okay? Very large detuning, okay? So if you look at this, I meant to hit this thing. If you look at it, there aren't that many oscillations. I mean, it's, like 15, right? But the coherence time is a microsecond. Okay, so if we go back to this one, you can see here our gating times were like, 4 nanoseconds. So if we could get 4 nanosecond gate time and a microsecond coherence time, we'd be in business. Okay, so then we asked the question, well, why isn't it happening? Like, why is it that why is we weren't able to get really high fidelities? Okay, and so basically we said, well, look, we should be able to get to really, really high fidelity by just increasing the gating speed, which is what I told you at the beginning of the talk. Okay, and here's just a little plot that shows you that basically here's the Rabi frequency, which is the gate frequency, and as you increase the amplitude of the drive, the frequency goes up, and if you can keep your coherence time the same, you should be able to get to really high fidelity. Okay. It turns out it's much more complicated than that, and because I don't want to go over, I think I'll basically skip this, except to say that we have an analytic theory where we can understand what happens when we try to increase the gate time. Okay, and there's one effect which is, there's one set of effects which have to do with the fact that, in strong driving, you don't get a sinusoidal response anymore. One of this is, there's a thing called the counter-rotating term. That just means that you have like cosine omega t, and you write it as 1/2 e to the I omega t plus 1/2 e to the minus I omega t, and then you only consider one of the terms, and then the other term is called the counter-rotating term, and that leads to these fast oscillations. And then there's also leakage, occupying that third state. It turns out that we can understand all of this analytically for the qubit, also in the presence of 1/f noise. Here's the theory, which just to show you there is theory, and we think we know what to do. Okay, but now I'll tell you the next step. All right. And again, if the theory works, which, and again, that's just a statement of like, if there isn't some other effect that we haven't taken into account, we will be able to, get 1 nanosecond gate time, so it's very high fidelity. And again, if we can get that microsecond coherence time and a 1 nanosecond gate time, that's a really high fidelity gate. Okay, but this we haven't implemented experimentally yet. But I do want to give you just some evidence that we know we can do this. Okay, so what Brunder did was that he actually plotted this. This is the decay time of the Rabi oscillations, which is the coherence time that I've been telling you about all this time, as a function of the slope of that dispersion curve. So here, this curve here. Okay, so you're looking at the qubit frequency and how it changes with detuning. the slope of that detuning. And I was just saying, oh, if it's flat, it's better, and if it's sloping, it's worse. And so, you know, if you double the slope, you have your coherence time, okay? And so that's an experimental prediction. And you know, and again, for most of the range, it works. So these data were all taken there, okay? But then it turned out that there's one point which he found, again, by tuning, where the qubit frequency is very, very slowly varying with detuning, okay? And you go there, and you say, well, this is just great. That's actually, this is the point you saw before, right? Where I had the really low Rabi frequency, but a really long coherence time. So he said, okay, Bronder, just jack up the amplitude, and we'll be in gravy, okay? And when he did, it turned out that the coherence time also went down. And the coherence time was precisely proportional to the Rabi frequency, and so it just didn't get any better. And so this now we understand. I'll tell you what it is. I think I have just enough time to do that without taking, you know, going over my time. And that is, okay, so we no longer have the situation where the qubit frequency is going up and down. He's tuned it away. But remember that matrix element depended on how much leakage state I had. And it's wandering back and forth. And so that says that the Rabi frequency also depends on detuning, okay? And so once you've got rid of the biggest effect, the next biggest effect comes in. And again, it's still coming from charge noise, but it's a different effect of the charge noise, an effect on the matrix element instead of on the qubit frequency. And so I was just like, oh, we're toast. But no, Wan-Chi Yang, who did this theory, he figured out that this is, now again, this is a recurring motif of qubits, is that we have these tuning parameters. We can up to now, we've just been modulating the detuning, but he noticed that if you modulated the detuning and tunnel coupling together, one made one makes the Rabi frequency go up and one makes the Rabi frequency go down. And so if you can do it in just the right ratio, you can also cancel that next effect. Unfortunately, before we could test it, the fridge clogged and the sample blew up, and so we have to wait. Okay. But we have a very clear-cut theoretical prediction that we should be able to get. You know, this again is a figure of merit of 1,000, right? Because if you think a pi over 2 is a suitable gate, then having the Rabi frequency divided by the this should be a gamma. I'm sorry. The decay rate be bigger than 250 is actually a figure of merit of 1,000. And we know we can do this because it has been done in other qubit systems where they have done 2 couplings, 1 tunnel coupling and 1 detuning. So that's where we are now. I hope soon we'll be able to, you know, test this theory, and if it works, we'll be in, you know, it'll be great. Oh, and I did want to do this because of the community here. So I've been telling you a story where everything was working, okay? But it turned out that, you know, I think I alluded at the beginning of the talk that things didn't work for quite a long time. And what happens when things don't work, it's not nearly as easy a story to tell as when things do work. And it turns out that the key thing in getting the experiments to work were understanding, like basically, a lot of complexity, because the way you do these experiments is you set up what you think is a qubit, and then you drive it really, really hard. And it turns out that, you know, that is what nonlinear dynamics is all about. So that qubit I showed you where it was just oscillating and, you know, it was like one frequency. Well, these were the initial experiments that they did. So these are the data, which you can sort of see. There's this is this data, and then we colored in all the frequencies. There's 1, 2, 3, 4, 5 easily visible frequencies. So if you don't know what you're doing, you get like a big mess, okay? And then here is, this is a different qubit that we did. Was done in Lieven van der Slijpen's lab, but he collaborated with us partly because he was just getting into silicon germanium and Mark had the samples. But then also, when they did the experiment, it turned out there were all these resonances. So he actually had 6 resonances. And what they happened first was that they, how did this work exactly? They found this one, okay? is it this one or anyway? They found a resonance. They tried to do Rabi. It didn't work at all. And then, you know, if your qubit doesn't work at all, you're just okay. But then we realized that there are other things that could be going on. And then they did a broader search. And then there were 6 resonances. And it turns out that one is a period doubling resonance, and one is a subharmonic. And then one, never mind. So it turned out that nonlinear dynamics was critical in getting the experiments to work. And again, sort of figuring out what's going on was really important. Once it's working, though, I mean, we're in this regime where everything's really very simple, and it's not obviously related to concepts from statistical physics. But it turned out that this was, I didn't realize, but my background was like, because any of those guys knew what period doubling was. They like hadn't even heard of it. So it was actually really handy that I had that background. Anyway. So I hope I've given you some sense of what's going on. I hope I've given you some sense that the field of silicon qubits is really advanced greatly over the last several years. I haven't talked about it here, but just in the last year or so, 2-qubit gates are starting to appear. And at this point, the best 2-qubit gates that have been reported are about 95% fidelity. Again, we're not there. But it turns out that in the superconducting qubits, like the IBM experience or whatever they call it, they only have 95% fidelity qubits also. So we're actually, I think we're at a stage where within a few years we'll be competitive with superconducting qubits. I didn't want to tell you about the qubit that we were making. We have not yet gotten the 2-qubit gate to work. We're working on that hard. We think that, again, that the good combination of fast gating and long coherence will be really useful for 2-qubit gates. And not only that, but we can turn the couplings on and off using the same tricks. And so we think that we have extra knobs that will help our 2-qubit gates. But we don't have any experimental results. So therefore, I didn't want to show them to you. Okay, but I want to tell you about like the ideas behind the qubit and why we think it's a good qubit, and also to give you some sense of the kind of work it is, where, you know, you do something and you think it's going to work, and then you realize that there's something else that you didn't consider, and you have to consider that. So it's actually, you know, pretty hard work. But we're really very optimistic that the field will continue to develop, and again, not by 2020, but at some point there will be a quantum computer that works. And I think I ended. Yeah, and so I just wanted to put up all the collaborators who did everything. Thank you.
Questions?
I have a couple of questions.
Sure.
When we are changing the potential, then we are creating higher number of these quantum dots.
Yeah.
So how long can we go? Like, how many quantum dots can we create, or is there any upper bound?
Well, okay, there's sort of different levels of that question. There's what has been accomplished experimentally so far that people have been able to manipulate. And, okay. Intel announced a chip, but the gossip on the chip was that it wasn't actually wired up. So we will leave that aside. The group at Princeton has demonstrated 9 dots in a row. Okay, plus a few more to measure. Okay. But the idea of the thing is, okay, so okay, in order to do the whole thing, okay, you have to come up with a better way of measuring than the point contacts, because the point contacts take up a lot of real estate. And there's a lot of work on basically using the gates also to do the measurements. And the way that works is basically, again, you know, so you would ignore so you could get rid of your ohmic contacts, and, you know, and you just do it by basically, you apply a little AC voltage to your gate, and then if you have an electron that is, you know, about to move into the other dot, it changes the capacitance of that gate, okay? And this has been demonstrated again on very small systems. But if that can be done on a large-scale system, then people think that's how you get to billions. The only problem then, okay, if the measurement works, and assuming that, there's so many things that have to be working, okay. The only problem is like, how do you get all your wires in? And then the idea is that you use the third dimension to bring your wires in, okay. So if you believe all that, then the two really serious problems that I think people haven't really for sure felt that they know what to do are getting the heat out, and then crosstalk between the wires. And now for the crosstalk, we're really banking on the superconducting people who are, they're in scale-up mode. They're trying to get up to, they're trying to get up to 100 now, but their roadmap is to do 1,000 in a pretty short time. And they have the same crosstalk problem. And so basically, just like with the qubit, we'll be stealing ideas with attribution, if they have a way of solving the problem. But we're sort of banking on them really helping with the crosstalk problem. Turns out the crosstalk problem is very different than in classical electronics. Because, so let me tell you why, okay. So in classical electronics, what happens is that, I've got a chip, and basically, again, it's, it's laid out. But you have sort of like an X and a Y, and you can sort of go halfway up to threshold in one and all the way up to threshold in the other. And so there are all these transistors along the way that don't go above their threshold, and then the one that you're targeting goes above threshold. So if you have a L by L chip, you only need 2 L wires to address everything. But in a quantum computer, unless we can come up with some way of doing, a trigger that triggered and then did the qubit, then you're stuck with L squared wires. Okay, so that's a critical thing. And again, it's possible in principle, because you could imagine that, right? Oh, we go above, then we, there's a little chipmunk that runs the qubit, and then, it goes above threshold and it runs the qubit. You could see it's possible in principle, but no one's doing that so far. Okay, and so those are the two things that make it so that I don't know. But getting the heat out is also, but again, somehow you feel you should be able to do that if you can get a qubit to work.
Okay. So the second question is a little, from different perspective. Like when you have 3 electrons in 2 quantum dots, so it's essentially, since beforehand you don't know which one is in which pot, so it's essentially in an entangled state.
Yeah.
So just by using that, can we do some further processing like key distribution or say quantum repeater?
Well, okay. In that context, the issue is that they're sort of talking to each other anyway. Because any spin singlet is an entangled state.
Okay.
So you've been like, wait, when you do the singlet and the triplet, you've been speaking prose all along, right? Okay. But the issue, can you do anything with it? And there you really have the things that makes entanglement interesting is if you can transport it somewhere else that's far away, and then you have this non-local aspect to it. So when the dots are next to each other, it's like, we think of it as, it's interesting from the point of view of the fact that it helps you solve the decoherence problem locally, but it doesn't help you in terms of being a resource. On the other hand, people have thought, this isn't something that we've done, but people have thought about if you start with an entangled state and then just take one of the electrons, which again, you can do with voltages, and just move it. How far can you move it before it becomes unentangled?
So it becomes very precisely the problem of controlling each side.
Yeah. And I was just reading a paper where, they were doing a combination of, spin manipulations and movements. And it actually looks like a really interesting thing to do. Because again, the problem is that it's really easy to make singlets as long as the electrons are right on top of each other. But being able to transport it is sort of, there's some work that's been done. So van der Sijpen has done an experiment like that, but in gallium arsenide. I don't know of an experiment where it's been done in silicon, but if you can do it in gallium arsenide, you can do it in silicon.
Thank you.
Okay.
Hi. Here.
Where are you? Oh, there you are. Hi.
I was just trying to get a sense for this figure of merit.
Yeah.
When you say you need about ideally 1,000, but
Yeah.
definitely much more than 100. What is it that makes like 30 not large enough?
Okay. Yeah. Okay. So it's the error correction is the issue. Okay. And so what Peter Shor showed was, okay, so let's just talk about error correction for a minute. Okay, so in your phone has error correction, but the thing is that transistors in classical electronics are so good that the error correction is extremely dumb. And it's all done using a thing called a parity bit. So if you have like a 16-bit number, there's like one more bit, and it's supposed to, and like the bits add up to some number, and it's either even or odd. And then the parity bit is like, oh, I'm supposed to be even, and if it's really odd, it just starts again. It just drops it and starts again. But quantum information is much more delicate. And so there's, first of all, like if you think of the qubit, there's like this thing of the analog of the bit, which is the Z component. That has to be right. But then also the X component, the off-diagonal component also has to be right. If those two are right, then you're okay because Y is equal to Z times X. Okay. But doing that simultaneously basically means that you have to have much more extra bits. And these are called ancilla qubits, or sometimes code size, all right? And so then it's basically you do the error correction, and the error correction has an overhead, and you make errors during the error correction. And so, and the error correction process is complicated enough that if your error rate is too large, you'll make more errors doing the error correction than you will correct in the original thing. Okay, so it turns out that so it's called an error threshold. The errors have to be less than some threshold, or else the error correction will just make things worse. All right, and the best known error threshold of a sort of error correcting code that people think they might be able to implement is 1%. And so that's where that 99% number comes from. But it turns out the size of the code grows very quickly as you get near the threshold. So the difference between 99.9 and 99 is huge in terms of what you'll be able to do. Because the idea is you just, you need to correct the errors. And then it turns out that that's like 90% of the size is error correction, which also motivates the Majorana's. But that's a whole separate talk, which isn't mine. Yeah. Okay. There's some, yeah.
The limitation of the classical computers is that it cannot just simulate time. That Feynman mentioned. It cannot, the classical computers cannot simulate time, but the quantum computers can actually simulate time because can you give some insight on this thing?
See, I was going to say, well, I'm just trying to build a thing that does it can simulate time. I have no idea what that means.
So,
yeah,
basically Feynman mentioned in his seminal paper, that's it. So I was just curious, so how would it be possible I'm not sure whether...
I mean, the thing I will say is that there's sort of two ways you can look at it. And again, I've been sort of immersing you in the hardware, and sort of how do you make hardware that you can do very well prescribed quantum operations, accurately. I mean, so in that sense, you might say it's engineering. Okay. But on the other hand, there's the separate thing of like, if you actually run a computation, then there's this thing of like, well, it can be interpreted, though some people say no, but, interpreted as, oh, you're doing quantum parallelism where you're sort of going over many paths. Okay. And that part of it is, you could sort of say, I can imagine, oh, you're doing the same thing over and over, and it's a different kind of simulation. But again, that's not something that I feel I have anything other than what I read on the internet to say. You know what I mean? Because when you're trying to build a thing, it's a very clear-cut thing of what you're trying to accomplish. But the interpretation of what an actual algorithm is, doing is a separate issue, but, the actual, physical steps that are required to do it is, completely well placed. I was brought up in the shut up and calculate school. You can tell. Okay. And so, and we have a very clear cut path where these sort of philosophical questions don't really, we hope to address them, right? Once we get hardware that works, then you can tell me what simulating time is and I'll go do it, And, but so that was a long way of saying, I don't know. Okay.